from Harvard, and he's going to talk about quantum dynamics of strongly correlated many-body systems.
All right, so I'd like to start out by thanking the organizers for invitation. It's great to be here. I think I've been here maybe a few years ago, but it's completely new generation now, so many new faces. So I will start out by giving kind of a little bit of a general introduction about what this research field is about. So, and this field is really kind of part of what we call a quest for controlling quantum world, where we start out by isolating and controlling some simple quantum objects, like individual atoms, individual spins, individual Josephson junctions. And then once these kind of systems are under control, we are trying to build more and more complex systems from them. And basically the kinds of things which we would like to do with this type of systems is study new physics with this engineered many-body systems, for example, create and probe new states of matter, which actually will be a subject of today's talk. But as of course all of you know, there is a lot of kind of buzz around is involving applications of these quantum technologies, applications to quantum information processing, communication, and metrology. And so I will focus today kind of more on the physics aspect, but I would like to emphasize throughout my talk is that actually these directions are very closely connected. So basically, better understanding dynamics of these many-body, kind of synthetic many-body systems allows us to actually design better schemes for quantum processing and for metrology. And on the other hand, by gaining more and more control, by basically building better and better quantum computers, we actually can study more and more physics. And kind of give you a little bit of this kind of, a taste of that. As you know now, there is a kind of a big quantum rivalry. Everyone can understand it in his or her own way. So you could think that this is like a rivalry between like nations who everyone wants to get the first quantum computer, or you can think about it as a rivalry between kind of different experimental systems, which ones will, arrive there first. But actually, I would like to encourage kind of more philosophical kind of Eastern perspective. So this actually is a rivalry between two different forces of nature. So the one force is a kind of is a controllability. So we would like to we would like to keep these systems under control. We would like to basically keep the evolution coherent and quantum mechanical. And on the other hand is this kind of challenge of scalability. We would like to have more and more of them. So and if as most of you know, these things are really contradictory. In many settings, not just in quantum mechanics, but also in classical world. So, for example, if you, put in one kind of organization, many bright physics graduate students, they will be very difficult to control. But nevertheless, so in quantum mechanics, that's a challenge which we have, and basically the current frontier is we kind of pushing with different experimental platforms, to build systems which are large enough, quantum enough, coherent enough, and programmable and controllable enough to kind of do tasks which classical computers cannot do. And the threshold for that is kind of typically in a range of maybe 3200 really coherent controlled quantum bits. But as I already indicated, my talk today will focus kind of not so much on quantum computing, but more on the physics aspects. And actually the first application of all of these things will be in the domain of physics. And one area specifically where this kind of scientific applications will emerge is really the area where I hope you guys are all interested in. It's basically a subject of the school. And this is the area of studying strongly correlated matter away from equilibrium. So basically, kind of the idea here is very simple. We are learning in one of our introductory physics classes about quantum physics that is supposed to be unitary. the dynamics of quantum systems supposed to be coherent. And indeed, we know that this is the case if we take single atoms or single molecules or single, Josephson junctions. We can always kind of time reverse the dynamics, and system generally will come with some limitations. Will come back to its original state. But then, of course, we also, in a second introductory class on statistical physics, we learn about things like equilibrium postulate, thermal ensemble, phases of matter. And actually, it does not really sort of go very well with this kind of basic concepts of this kind of unitary quantum physics. So basically, what we would like to do with this kind of medium scale quantum systems, we would like to really study this interface. So we would like to understand, for example, how isolated quantum systems thermalize. When do they thermalize? What's the dynamics of thermalization? And basically, this all goes, under the name of really understanding kind of many-body dynamics of complex quantum systems. It's of course related to eigenstate thermalization hypothesis, and I guess Rahul will talk about in details. Things like role of localization, long-range interactions. They're all these kind of things which are under study. But so, what are the goals of this? The goals are really to try to understand, dynamics of these kind of isolated systems far away from equilibrium, right? So we know, I think we understand quite well, the concepts of, kind of phases close to equilibrium, the concepts of phase transitions, but can there be some stable phases very far away from equilibrium in the corners of Hilbert space, which actually are not really accessible by conventional kind of, physics, systems which are in contact with the thermal reservoir? And actually, if we start kind of get a better grasp and better understanding of this kind of non-equilibrium quantum phases and quantum states, this perhaps will actually help us to really develop new applications, and applications like quantum computing, quantum information processing, and quantum metrology. Okay, so that's kind of the general theme of this research. And so what I'd like to do is I'd like to basically illustrate all of these ideas in my 3 lectures using basically 2 examples. And these are the examples from our recent research. One will involve exploring quantum dynamics in the Rydberg atom quantum simulator, which is composed from individually controlled neutral atoms, so where we can create regular array and we can control atoms one by one. At the same time, I will talk maybe in the second lecture today or certainly tomorrow about another quantum system which is also quite isolated, but this is a system which features a lot of disorders. So these are basically a system of impurities, spin impurities in black diamond, which are so dense, that they actually, the interactions between them kind of dominates. So these are dipolar impurities interacting through the long-range interaction, and basically, in both of these systems, we will study, this kind of, non-equilibrium quantum dynamics. Either dynamics, not too far from equilibrium, or we push the system very, very far from equilibrium, and we ask if there is some kind of emerging patterns, if there are emerging kind of new stable states. So I should say that, in my choice of the subjects has been also in part motivated by that, and on all of these directions, Princeton theoretical physicists have made important contributions over the last multiple decades, and I will illustrate when it is appropriate. So in fact, I was hoping that David Hughes will be in the audience today to help me answer some questions. But anyway, actually, I would like this kind of lecture series to be kind of informal, and actually, in fact, I will pause, at times. So there are actually a lot of material. So, and I think there's a mixed audience. So there's kind of theorists, experimentalists. I was told I should kind of, maybe try to sort of aim for all. So maybe actually at this point I will stop, and I have not really communicated much of the information so far, but nevertheless I will stop and ask, if there are any questions. Are there any questions about the introduction? Or is everything clear? so everything is clear, but don't, okay, anytime, don't hesitate. So I'd like to actually promote this kind of interactive style. All right, okay, so then I will actually now start talking about this first topic. And so basically, here is an outline what I'd like to cover on this first topic. So basically, I will tell you about new approach for building kind of synthetic scalable quantum systems, which will make use of basically atom by atom assembly of strongly interacting matter. And these strong interactions will be based on promoting the atoms into these Rydberg states. Then I will tell you how we can use this kind of platform to build a programmable quantum simulator. And using the simulator, I will actually tell you about how we can engineer different phases which break different types of symmetries, and how we can explore the phase transitions in this kind of system. And then I will actually give you two examples studying non-equilibrium dynamics using a system. One of them would be exploration of quantum critical phenomena using the so-called Kibble-Zurich mechanism, quantum Kibble-Zurich mechanism. And another one will be studying, it's actually will be focused on a first discovery which we made with this system, and this will be kind of emerging quantum dynamics, which now is known under the name of ManyBody quantum scars. So it's actually related to ManyBody quantum chaos. Okay, so kind of the goal of this work, the ultimate goal is really building quantum processors based on cold neutral atoms. And as compared to all sorts of other systems that people are studying, the cold atoms have two major advantages. So first of all, they can have excellent coherence properties. So for example, like the modern optical clocks, the best possible optical clocks which people build nowadays, is based on this kind of cold neutral atoms. And the second important advantage is that it's actually very easy to create a large number of identical neutral atoms. In fact, those in this room, there are a lot of molecules flying around. So in principle, you can encode qubit in each of these molecules. Will be a lot of qubits, and they are all here. So, but why we are not why is it not done in a routine basis? There are kind of this is because of two challenges. So first of all, generally, atoms in a gas phase interact weakly with each other. And basically to make, for example, logic gates to build quantum machines, you need strong interactions. And the second reason is that atoms are actually hard to control individually, at least in large numbers. So for example, all of these atoms which are flying around us, they're sort of not very useful for the purposes that we are discussing here, is because we can just not track each other's atom motion. We can, not control them. So these, of course, have been problems which have been well recognized for several decades. And there are a couple of approaches to kind of address them. One of them involves involves loading the kind of ultra cold atoms in optical lattices and using the techniques of quantum gas microscopy. These are kinds of techniques that Wasim Bakr actually pioneered while he was working with Marcus Greiner at Harvard. Wasim is now a professor here. And these are beautiful systems. I must say these are very complicated experiments. They were very involved. And you can actually load in these lattices a large number of atoms. You can basically completely get rid of entropy from those systems, so they can be really very, very ordered, close to absolute zero temperature. But as I already mentioned, those involve typically very complex experimental setups. So also individual atom control is possible, but it's actually very difficult. And last but not least, these experiments, they involve evaporative cooling. So to create this kind of ultra low entropy state, you have to the atoms have to undergo a process of evaporation, and it's actually a very slow process. So basically, what means is that the cycle times typically are kind of a fraction of the minute. So, but then there is another approach, which I would say bottom-up approach, and where you can basically just use focused beams of light just kind of to begin with, start with atoms which are individual controlled. This approach uses so-called optical tweezers. And in this approach, you can actually have much shorter cycle time. And the setup is much simpler. And basically, this approach is built up to kind of control individual atoms to begin with. But at least until recently, this approach was not very scalable. And this is because in the way how you kind of load these optical tweezers is kind of probabilistic. So what you do, you start with the gas of pre-cooled atoms, and then you shine light beam in that. And then, this focused light beam, attracts the atom. And if the trap is very tight, then it is sufficiently, its volume can be sufficiently small that it actually can load at most one atom. But what will happen in practice is that this loading will be probabilistic. Sometimes there will be a loaded one atom, sometimes there will be no atom. And so basically, if you start, for example, with some kind of complex arrangement like what is shown here, and try to load it, then on each given shot, you will have, some atoms, some traps which are loaded, and some traps which are empty. What it means is that if you would like to really experiment with a large kind of assembly of traps, loaded traps, you have to try many, many times before you can actually load it. And this actually becomes, what it means is that, at the end, if you want to work with, something like more than 10 atoms, this, this requires like very long time to actually just start the experiment to load this up. Okay, so motivated by this consideration a couple of years ago, we started kind of developing a new approach to this problem. And this approach, kind of basically the idea here is to remove the entropy by observation. So in this approach, what we do is we follow this kind of optical tweezer path. So we start with the gas of pre-cooled atoms, and then shine these focused beams of light, tightly focused beams of light in a vacuum chamber. But we don't just shine one of these beams of light. We at once, shine like 100 of these focused laser beams. And then what we try to do is simultaneously load all of these tweezers. But of course, due to this probabilistic nature, what will happen is that some tweezers will be full after one approach, and some will be empty. And so this clearly there is some entropy in the system. So to get rid of this entropy, what we simply do is we take a picture of these atoms. We take an image and figure out which traps are full and which are empty, and then just remove the empty trap and then rearrange the full traps in any way that you desire. And so at this point, we start with completely regular array with atoms which can be prepared, with very high fidelity in well-defined internal states. And then what we need to do is we need to engineer interactions between the atoms. So typically, the separation between these tweezers are on the order of maybe a micron, and from 1 micron maybe to 10 microns. So this actually is quite substantial separation between the atoms, such that when the atoms are in the ground state, the interactions between them are completely negligible. So to engineer interactions, we're actually exploring two different approaches in my lab. One of them involves coupling the atoms to the photonic crystal waveguides, and basically uses photonic crystals to engineer interaction. It was actually an experiment which was started by another Princeton faculty member, Jeff Thompson. And we are continuing that, but actually today I will focus mostly on this second approach, where we actually take these atoms and excite them into highly excited Rydberg states. So in these Rydberg states, the atoms start feeling each other's presence, they start interacting, and this is the approach which involves collaboration between my group with the group of Marcus Greiner and Vladan Vuletic within our Center for Ultra-Cold Atoms. So here is kind of an experimental setup. So it's actually, you don't really need to understand all details, but the key element is this shown here. It's so-called acousto-optic deflector. So this is a device which takes as an input one laser beam and a number of RF tones. And what, for each of these RF tones, so what happens is that this laser beam is deflected by a certain angle. So it's actually kind of a device similar to that which is used for barcode scanners in a supermarket. And this one is like but it's what it can do here is can just starting with one laser beam, create an array of these optical tweezers, which we then focus on a vacuum chamber, and then through the second objective, we basically take the picture of these atoms after loading, figure out which traps are full, which are empty, and then activate the fast feedback loop where we just kind of change this input here, changes RF tones, which will start kind of moving these atoms around and creating this ordered arrays. So this is actually experimental team which has been built and kind of run this experiment, I think, over the last 3 years or so. That's when we start. So here are some images where we start, in this case, with 101 trap and just load the atoms. And what you see initially, there is a lot of entropy, and then what we are doing here is we are just trying to move all field traps to the left to create a kind of ordered array. And so in this case, you see that after the motion, there is the array is much more ordered. So here is maybe one atom missing, but basically there is also high chance that you can create completely ordered array. And of course, we can also vary the geometry. So for example, we can create clusters of 2 or clusters of 10. And once again, these are single atom images. They kind of immediately show you how well we can prepare this kind of state. So here is, for example, one atom missing, but it's the only one atom missing in all of these attempts. So here is one atom missing, but once again, it's the only one atom missing. So this kind of allows us to prepare these states with very high fidelity, and we can also vary the geometry with repetition. So I must say, so simultaneously to this work, there has been also work by a group of Antoine Bravet, which actually created this kind of arrays, which were not as big, but they have done it in 2 dimensions already, and actually by now they have done it in 3 dimensions. And I will comment maybe later in my talk what this implies. At this point, we create these arrays of atoms, but this is completely classical physics. They are non-interacting, right? So to make them interact, as I already mentioned, we excite these atoms into these so-called Rydberg states. So these Rydberg states are kind of hydrogen-like kind of orbits of atoms with large principal quantum number. And there are two properties of Rydberg states which we explore, which are very important. One is that Rydberg states have very long lifetime, but also they have very strong interactions with each other. So basically, kind of in this typical Rydberg states, which we excite with n on the order of 100, the size of the orbit is something like close to 100 nanometers. And of course, once this the size of the orbit is so large, everything, all interactions, everything, increase dramatically. So in fact, for n equals 100, the van der Waal interaction, 1/6 interaction, is larger than that for the atoms in the ground state by something like 14 orders of magnitude. So 14 orders of magnitude is a large number. And, of course, one can make good use of that at this point. So one of the consequences of this kind of interaction is the effect called Rydberg Locate. So this, in fact, will be very important throughout my talk. So I would like to kind of explain it carefully. So the idea here is the following. So suppose you start with 2 atoms now which are very far away, and suppose you drive them resonantly. So what will these 2 atoms do with the coherent field? Test for the people I sleep. So what will happen with these atoms? So if you take atoms, and just let's take one atom, if you apply, that's like a quantum dynamics, not 101, but it's like kindergarten, So what will happen?
Rabi flop?
Yeah, exactly. So it will undergo Rabi flop. It will be excited and then de-excited. And so this will happen if these 2 atoms, if they are far away, they're not interacting, they will just undergo Rabi flops. And so now let's bring these atoms closer and closer while still trying to excite them both. But so what will happen at some point, this interaction will take over. And so this interaction basically corresponds to energy level shift for atoms both in the excited state. So what will happen, basically this doubly excited state will start shifting, and actually at a distance of about maybe 10 microns or so, it will just, completely explode. So if you are still trying to basically drive both of these atoms with narrow band laser, what will happen at this point is that you will be able to excite one of these two atoms, but not both. Right? So basically what will happen is that this doubly excited state will shift out of resonance. And so basically, and that's the kind of an essence of this phenomenon of the Rydberg blockade. So basically this Rydberg blockade blocks simultaneous excitations of two atoms when the atoms are separated by some distance below this so-called Rydberg blockade radius. So the Rydberg blockade radius, of course, depends on the Rabi frequency with which you excite, but it also depends on this interaction. And this interaction, basically, is a dominant, plays a dominant role here. So what does it mean? And actually, it turns out that this effect kind of generalizes to also ensembles of atoms. So if it's not just two atoms, but there are like n atoms, but they are kind of densely packed within this region below this blockade radius. So what will actually happen? Now that's a question. What will happen if you start with this ensemble of atoms in the ground state, right? And you try to drive them, you will try to excite them in the Rydberg state here. So what will happen under these conditions of this Rydberg blockade? How will this cloud respond? So it's slightly more advanced question, but now it's 101. Okay, so remember at this point, we can excite one, we are still free to excite one atom, but only one, right? So all of these kind of multiple excitations are completely shifted away. So what will happen with this cloud? Suppose that you excite it homogeneously.
You'll undergo a slower oscillation.
Will undergo slower oscillation. So there are two parts to the answer. So this cloud will undergo Rabi oscillations, and these Rabi oscillations will be slower. So this answer is partially correct. It's about 50% correct. So it is true that it's actually at this point it's still a fully coherent process. So there should be some kind of dynamics happening, and it should in fact, the answer is it will be coherent dynamics. But remember in this dynamics, you will be able to excite, at most one atom. So basically the only accessible states are states with no excitation and one atom excitation. And now the question is about the speed. So why do you think it's a slower? Why is it a slower? Any other ideas? So what are the accessible states? The accessible states are all atoms in a ground state. And then there is an accessible state with just kind of single atom kind of manifold, right? And of course, you in principle can excite any kind of combination, any superposition of the single excitations, but actually the symmetry of the excitation laser will actually determine one specific combination of the states. So for example, if this laser is homogeneous, you will excite symmetric superposition, right? So basically, okay, so that's a picture which will emerge. So indeed, what this laser will do, it will drive the transitions between, all of these atoms in a ground state and one atom in the excited state. And so the system will undergo Rabi oscillations between these two states. One is simple state and one of this kind of collective state. In this case, in the case of homogeneous excitation, it will be just symmetrized superposition of all of this. But actually, what happens is that the Rabi frequency of this oscillation will be actually faster and not slower. So why is that? So let's kind of build a little bit of intuition. Well, like once you try to excite this state, remember you have n absorbers, right? So if you kind of try to drive it, the probability to absorb a photon, one photon, will increase by n, right? So what means Rabi frequency, which is kind of square root of this probability, should actually scale like, square root of n. And it's kind of very easy to see it also if you write down the Hamiltonian for this system. So what is the characteristic, basically sort of the idea here is that, in this kind of, mesoscopic scenario where, everything is, put under this kind of umbrella of this dipole blockade radius, you undergo basically coherent dynamics involving states with 0 excitation and 1 excitation, and actually characteristic Rabi frequency will scale as a square root of n. Does it make sense?
Why the singly excited state is the denominator is not square root of n?
Wow, that's a very good point. It is actually an error. This slide has been it should be normalized, of course, by square root. So this slide have been seen by maybe, I don't know, thousands of people, and you are the first one to point this out. So, okay, any other questions? Okay, so that's kind of the basic idea, and this idea is not new. It's actually almost 20 years old now, and it has been kind of explored in many different contexts, from quantum information to ManyBody physics, to actually also some very interesting work involving quantum nonlinear optics using this technique. But so what I'd like to do now is to kind of show how to marry this idea with this, arrays, with these Rydberg arrays. And in the first kind of instance, what we would do is we would just excite these arrays homogeneously. So we would drive them from the ground state to the transition with n equals 70. So this is a 2-photon transition, but it's actually not so important. So, and what we can do now is we can do these experiments, initially on kind of small clusters. So for example, in this first case, we will prepare the cluster of atoms, which will be separated by, large distance, individual atoms, right? So in this case, this is just individual atoms. They will undergo Rabi oscillations between a state with 0 excitation and 1 excitation, or we will prepare clusters of 2 atoms. And in this case, what you still see is that at most we can excite 1. But the Rabi frequency changed a little bit, or we can create a cluster with 3 atoms, and then we have this. Also, still can excite at most 1, but but the Rabi frequency again changed, and actually one can plot now this measured Rabi frequency, and what we see is that actually it follows this. The square root behavior up to the cluster size, which corresponds to this blockade radius. Right beyond that, there are some deviation, and actually now maybe I know why this square root was missing. So it's kind of shows up very clumsily here. So probably was deleted accidentally for our aesthetic purposes, in the previous slide. But anyway, so this. Basically, so this phenomena essentially involves this kind of Rabi oscillation between the state where all atoms in the ground state and one single atom excited. And as I already indicated, this in principle, this is not a new kind of observation, but what is kind of new and unique is that we can really have very high fidelity control of both single atoms and this kind of blockaded, entangled Rydberg states. Yes?
I may have missed this, but how do you know that there's not multiple superposition states like that in that, at that energy?
Okay, so at this point, what we see is that we only see that at most there is 1 atom excited. Right?
Yeah.
But what you are saying, what you're asking is, okay, so we know that, there is 1 atom excited, but in principle, for example, here what can happen is that there could be different, amplitudes, and in particular different phases,
Yeah.
right? And so from this experiment alone, you cannot determine that. So you need to do a different experiment, and
So
that's
you treat some group of states as like one.
well,
level
okay.
of
So basically, you need to do some kind of like a quantum tomography experiment, and actually, this is an example now that I will show. So basically, so like to really verify that the state which we create, is an entangled state, you need to do more than just measure the number of excitations. So specifically, let's kind of focus now on just two atoms. And let's just try to do this blockade experiment. And basically, what one can do here is that one can measure probability with both atoms in the ground state, zero excitation, probability of one atom excited. One can also measure them individually, of course. And then you also measure the probability of two atoms excited. And what you see, for example, here on this two-atom case, this probability of two atoms excited is basically in a noise, right? So this blockade works very well. But the thing which actually is maybe the hardest is to really be able to distinguish, for example, in this case, this state here with plus phase, with plus sign from the state with a minus sign. So basically, you need to measure a parity of the state in this case. And in order to do that, what one can do is one can first prepare this kind of state, and then, for example, apply some kind of effective magnetic field, or what we do is we kind of shine a laser beam, of resonant laser beam, which introduces the so-called AC Stark shift to one of these atoms. And kind of what it does, it starts basically rotating the phase of one of the atoms. And what should happen is that this kind of W state should go into this kind of so-called dark state, right? So basically, this application of this phase should cause these two atoms to kind of rotate to each other. But note that our excitation beam is homogeneous, right? So what it means is that it only couples to this state, right? So basically, a combination of applying this phase shift and then trying to kind of de-excite this superposition which we create actually allows us to really measure this parity. And basically, by measuring this parity, we can actually, measure this parity oscillation, which basically allows us, the combination of these two data really allows us to make a kind of quantum state tomography, kind of nail down if we have this entanglement. And actually, this entanglement fidelity is actually, which we measure, is quite high. It's basically close to 100%. So the kind of main uncertainty here is related to the fact that our kind of atom state detection efficiency is now imperfect. So the fidelity of atom state detection is actually about 95%. So this is dashed lines that they show sort of the best fidelity which we can obtain, knowing our infidelities of the state detection. Basically both this entanglement fidelity and this gate time, which is about 100 nanoseconds, can be improved. And actually, there are some interesting things which we have already observed in this first experiment. For example, the lifetime, the coherence of a Bell state, of a state which we prepare, turns out to be longer than the coherence of individual atoms. You can ask, how can this be? So it turns out, there's a little bit of technical details. So a lot of the challenges in controlling this kind of processes associated with a laser phase noise. So if the laser phase is not stable, it can introduce some additional decoherence. And in fact, this is one of the things which we have improved here. We use the techniques that our friends in atomic clock community are using to actually improve this phase noise, and that allows us to, for example, push these fidelities to this kind of high values. I must say that this actually represents a substantial improvement to what people have done previously, right? Okay, so at this point, so this is sort of like was a little bit of a review of kind of a platform and a little bit of technical details. Maybe I can slow down here and ask for questions, because now I will start talking about ManyBody physics, so I will accelerate a little bit. Yes.
You said the fidelity below is due to the your inability to measure. Is that due to the basically the state you're creating, the initial state you're creating is a mixed state, or is it also at later on?
No, so okay, so let me just maybe explain a little bit. So the way how we make measurements of atomic states. So the initial arrays which we prepare, and including the internal state preparation, are very high fidelity, and this is in part due to our atom rearranging procedure, but also what we do is basically, the way how experiment works is that we always take 3 images. One is the first image before sorting. Then we sort atoms, and we take a second image to basically verify that we sorted well. And what it means is that in cases when we don't sort well, we can actually disregard it. It rarely happens, but like it allows us to basically purify our initial state to very, very high degree. But then what we do this Rydberg excitation, and the important thing is during these Rydberg excitations, we actually turn off our traps to avoid the decoherence. So atoms are sufficiently cold, and during this typical kind of time scales, which we do experiments, let's say up to 10 microseconds, they don't move. So, and then, after that, what we do is we turn on the trap, and when we turn on the trap pushes away Rydberg atoms and captures the ground state atoms. And that's our detection procedure. So basically what we detect is we detect remaining atoms, ground state atoms after this procedure, and this gives rise to kind of state-dependent measurement in the Z basis, if you want. So, this actually turns out that this pushing of Rydberg atoms is not perfect. So it actually has this, maybe 5% or so infidelity. This method is actually very simple for a measurement, but it's actually, it's not ideal. We know how to improve it, and actually we're already in a new generation of experiments. We improve this detection and fidelity. The way how we do it is we de-excite both Rydberg atoms and both to a different hyperfine state of our atom, and then just take an images, and that should basically result in detection fidelity, which are rival, almost any platform here.
So in that method, you could actually do the process again.
Yes, so in that process, it will be very similar, except for this now, this detection and fidelity will be, will be a fraction, a small fraction of percent. So, yeah.
Is it possible to directly excite the dark state?
Well, okay, so this dark state is basically, it's by definition of the dark state, the answer is no, right? Because what you could do, you could, for example, change. So these states, bright versus dark, is basically determined by a relative phase of these 2 excitation lasers, right? So if, for example, you don't excite them in this way from the side, but you excite them from this direction, then you can excite any state, right? By just playing with the phase and playing with the amplitude for that matter.
So what do you mean by coherence of individual atoms? Is this if you keep on driving single Rydberg
No. So it's that's kind of an interesting. So if you guys are into, so I have a slide. There. So to do the coherence of individual atoms. So actually, maybe it's not the most ideal, but anyway. So okay, so let me just say what happened. So this is kind of a new development. So this is sort of typical Rabi oscillations which we observed last year, and these are the Rabi oscillations which we observe now. So this envelope is actually kind of a decay expected from things like spontaneous emission, which is so. And basically, the improvement here was the improvement of the laser phase noise. So it turns out that it's kind of a little bit technical. So when laser, so laser phase and laser frequency, usually jitters a little bit, and there is a very well-known technique how to kind of stabilize that. And what you do typically, you just lock these lasers to some, very high It's very stable cavity. But actually it improves kind of a long-term stability of a laser dramatically, but it actually turns out that, you know, it can, like this feedback loop can create a phase noise with frequencies on the order of maybe megahertz, which are actually very relevant for the excitations. And this effect, you know, has been sort of in this kind of experiments have been overlooked, but actually it turns out this has been noticed in atomic clock experiments, and there are ways to kind of filter this phase noise. And in fact, that's what we actually have done here. But you know what happens now is that we can do, for example, things like you know, spin echo experiments on both single atoms and atom pairs. And what happens is that, you know, the spin echo experiments are sensitive to this kind of phase noise for single atoms, but not so much for atom pairs, because for atom pairs is like it's a common noise. So once you excite, you know, then they're basically subject to the same noise. And so what it really kind of what it means is that, for example, the dephasing of the individual atoms is actually much faster, you know, even with improved lasers as compared to dephasing of this atom pair. And I think that indicates that even though we fixed this problem to some extent, but we did not fix it fully.
So this is because it's phase noise in your global.
It's a phase noise, exactly. So this phase noise suppression, which we had, you know, was kind of already enough to do that, but apparently it's not. That's what we believe, it's what we think. Because there are other mechanisms, like for example, atoms move a little bit, there is some Doppler effect. But this Doppler effect in spin echo can be very effectively cancelled out. But so, you know, basically, just to kind of give you, you know, maybe also give you a little bit of a sense, you know, like in these experiments, I will talk now about the physics we are doing. So, but we're continuing doing physics, but we're also doing these technical improvements at the same time. And it actually turns out that many of, for example, this phase noise, well, important for single qubit control. For many of these kind of measurements, by ManyBody measurements, actually not so important, you know. So, but or it's important, but maybe not as directly. Any other questions? Wow, I used up my hour. Anyway, okay, it's okay. So I think it's more important that. All right. So let me then, you know, at least start. So when is it? When is we supposed to stop?
12:15.
Okay, good. So it's not too bad actually. All right. Okay, so all right. So let me now then, you know, at least start talking about kind of ManyBody physics, and you know, I will do that in the context of using this platform to realize a quantum simulator for kind of an Ising type spin model. So this is basically kind of a transverse field Ising model. Well, has both transverse and longitudinal field, but actually it's kind of written here in a little bit different way. And I would like to maybe, you know, slowly go through this kind of notations and through the phase diagram. So essentially, so let's kind of imagine that we have an array of these atoms, and they interact with each other, and this interaction is described this Vij. And I would like to kind of describe each atom by this index n, and this n will be essentially a number of Rydberg atoms on site I. So on each site, you can have either 0 or 1 Rydberg atom, and then I will be driving these atoms. So this driving will be with this field pointing effectively in the x direction, so laser driving. And I will also have some laser detuning for each atom, you know, and this will be effectively in this modular field along the z direction. And finally, I have these kind of interactions. So, I mean, this model is equivalent to the Ising model, but up to basically some single particle terms. So, but you know, because of this blockade mechanism, so only atoms in an up state interact with each other. That's when it's convenient to. It's the reason why it's convenient to write it in this kind of way. So to get some intuition into this model, I would like to first talk about the ground state properties of this Hamiltonian. And I will quantify these ground state properties on this two-dimensional plane. On one of them, I will basically plot my detuning. So this detuning basically plays a role of a chemical potential here. And on the other axis, I will plot this kind of interaction range. So this will be like it's basically how many of the lattice sites are blockaded, essentially, right? You know, kind of simplified terms. So, okay, so let's talk about the ground state, and let's first, neglect these interactions. Suppose interactions are so short range that they are basically irrelevant. So then, the ground state will be very easy. So it will be only determined by this chemical potential. So if this chemical potential is negative, then basically all atoms should be in the ground state, right? So then, all n should be 0. But, if delta is positive, then of course I would like to have as many excited atoms as possible, right? All of my atoms should be in the excited state. So, but at this point, we are neglecting interactions, of course. So now we talked quite a bit about blockade. So basically what blockade should do, it should prohibit excitation of the atoms which are within this blockade radius. So if, for example, blockade extends over the kind of, let's say, 2 lattice sites, So in this case, this state, will not be accessible, will not be energetically favorable. So what should happen is that, instead of that, basically I should be able to create a state where, every other atom is excited. So I excite as many atoms as possible, right? But, I cannot excite nearest neighbor because they are blockaded. So, so it actually turns out that, like once you introduce this kind of constraint, and this constraint is essentially a product of ni and n plus y is equal to 0. So in this case, this model can be mapped into something which is called hard boson model. And that actually model has been studied by Subir and colleagues. And they actually, have sort of investigated, phase diagram of this model, which actually is quite interesting. So, and specifically what this model predicts is that there should be a phase transition here into this state where there is basically no order, this state where all of the atoms are in the ground state. It's kind of referred here as a disordered state, to the state where the Z2 order is broken. But actually, it becomes even more interesting if we increase the range of interactions. If, for example, our not only nearest neighbors are blockaded, but also a second nearest neighbor are blockaded. So in this case, you actually can break a Z3 symmetry, so it becomes Z3 order. So every third atom can be excited, or you can go to even longer interaction range, and then you can break Z4 symmetry, right? And so it turns out all of these kind of states have some phase transitions which actually are unique. They are very different from each other. And basically what I would like to do now is tell you how we study these transitions. So the basic idea. So are there actually any questions about the phase diagram? Is it clear? So it's kind of very intuitive, right? So the way how we will study these phase transitions is by using adiabatic following. So basically this kind of state where all atoms are in the ground state, that's very easy for us to prepare. And we will start, basically, we'll shine the laser light initially, which will be detuned with negative delta, right? And then we will start basically, then slowly changing this detuning with the hope of entering these transitions, and by picking which state, Rydberg state we excite, by picking what the relative position of the atoms, we can really try to hope to enter each of these different phases. So initially, in the simplest case, we will focus on a case where long-range interaction is negligible. So for example, we can pick our atom separation and Rydberg state such that the nearest neighbor interaction is much larger than omega. Than the driving Rabi frequency, and the next nearest neighbor interaction is much smaller than omega. Right? So in this case, we hope to enter this Z2 ordered phase, and this is a typical pulse sequence. So we shine light with negative detuning, turn on this laser pulse, and then just go across this transition slowly, and and then go all the way into hopefully ordered phase, and then just take a picture of atoms. So here is this kind of transition in an array of 13 atoms. So one can look and kind of study them in a different way. So here is, for example, initially was a picture of 13 atoms, and then after this transition, what we see is every other atom is missing. So that means that every other atom has been excited in Rydberg state. We can also stop somewhere in between, and in this case, what you see is that this kind of two states compete, right? So you have either disordered state or ordered state, but system cannot decide. So there's a lot of fluctuations here. We will study this fluctuation just in a moment. Or you can also make an average. You can just look here and make an average of many transitions. What you see is that you have this up down, this kind of antiferromagnetic order corresponding to Z2 symmetry breaking. But as I kind of indicated, we have access to these other states also. So in particular, by either changing the Rydberg state, which we excite, or just moving atoms closer together, we can try to enter these other states. And indeed, by changing atom separation for a fixed interaction, we effectively change the interaction range. And then what we can do is we can either enter the state with the broken Z3 symmetry, or we can enter the state with broken Z4 symmetry. So, so basically what you see here is that we can, by programming this interaction strength, we can really try to sort of engineer desired symmetry breaking. Just before we kind of go on and study this phenomena in much more detail, so one could ask a question, how well does this, quantum simulator work? We believe we can write this Hamiltonian, but is it really coherent? Can we quantify its behavior? So in the case we study, for example, when we look at this, transition to Z2 ordered state, the nice thing is that actually we know the state from which we start, and we know the state where we should kind of eventually arrive to, right? So we can just ask the question, what's the fidelity of this kind of final state which we create? And on a small system size, what we can do, we can actually try to model this just by using exact diagonalization, directly numerically simulating Schrödinger equation. And for this small system, for example, 7 atoms, what we see is that like this actually overlap of many body states. So initially you had kind of 0, 0, 0, and actually this, I think this is due to this, the fact that it's not 1 is due to detection infidelity, which actually have been accounted for here. And basically what we see is that we have nearly perfect overlap, in particular when we take this detection infidelity between the kind of single atom, between the numerical simulations of this many-body 7-atom state system and our results. But of course, what we would like to do, we'd like to go to larger system size, and so in this case we went to up to 51 atoms, so we can actually prepare arrays maybe now up to 60 atoms or so. But for 51 atoms, it of course becomes a very large Hilbert space, and it's impossible to simulate, but we can still make measurements. And actually, what we see is that as we kind of increase the system size, our ground state probability, the probability to create this perfectly ordered state, up, down, actually decreases exponentially. So in these experiments we've done last year, still we observed some significant overlap, about 1%, even for the full 51 atom system. But actually what's interesting is that you can also look now at individual kind of microscopic states which occur. And this is like a histogram, so actually most of them, it's a very large Hilbert space, so most of these microscopic states never occur in the final state product. Then, a number of them occur just maybe once, and, basically, most of them never occur more than, I don't know, 5 times out of this entire, big number of realizations. But there is one outlier here, and this outlier is the most probable state. And this is this is the state which is actually this is this perfectly ordered state with these 51 atoms, up, down, up, down, up, down. Moreover, so this 1% is actually not a small number in view of this large Hilbert space, but with this improved laser system, the stuff which I described before, this number is like 10%. 100% is a very large number, given that you really operate with this kind of big quantum system. So, but actually, in terms of like this kind of measurement, we used to really quantify how our system works. But in terms of, let's say, kind of many-body phenomena, we are interested to access what's it, extensive. So I'm always mixing intensive quant. So we're not like interested to know exact overlaps. We're interested to know, for example, excitation densities and stuff like that. And actually, that we can do very nicely because we can just directly, for example, we can start with 51 atom array, and we can just, you know, take a bunch of these images, and we just can look at these images. You know, so for example, I said that, you know, in some cases we have these perfectly ordered arrays, but you know, but then in practice, you know, for most of the cases, you'll have images like this. You'll have like a string, an ordered string, and there is here some defect, you know, and then there is another perfect string, and there is some defect. So these strings we'll call domain walls, right? Because these are ordered domains, and these are domain walls. And what we can do is we can, for example, look at a number of domain walls, an average number. We can look at variance. We have an access to full distribution functions of these domain walls, and that way we can, for example, try to nail down where the phase transition occurs, right? So here is the mean number of domain walls as we change our detuning. Again, it's a slow change. And what we see is that this varies, mean number of domain walls varies smoothly, but actually a variance of domain walls, the fluctuation domain walls, you know, has a peak at some value, and this is a peak which should be right at the point of the phase transition, right? Because that's where a system cannot decide which state to go to. And actually from here we can really nail where phase transition occurs, so it turns out that this value is in a very good agreement with this result of final size scaling analysis, which Subir and others have carried out. Okay, so at this point, you know, I gave you kind of a little bit of a background, you know, what sort of Hamiltonians we can access and how we can study them. So I'd like to now kind of go and to actual, you know, the main subject of my lectures is probing kind of non-equilibrium dynamics with the systems. But maybe before we kind of go on, maybe let me pause here and ask if there are any questions. Yes.
How do you know from Hamiltonian which atom you are exciting? Because you have these probabilities that are varied. So maybe cost to excite one specific atom may be more than when you.
Okay, so what we do is, of course, we, you know, like we calibrate our like, so these probabilities are controlled by basically laser intensity at each specific atom. And what we do is we can actually, because we can place atoms wherever we want, we can look at each atom individually. We can basically calibrate the Rabi frequency to at each atomic position to a very high degree. So in fact, we can actually put a number, so our variance in the Rabi frequency across array is less than 1%. So, and we can do it in situ, right? Right, so that's kind of part of the control system. But of course, then the atoms, once you excite many-body systems, and atoms interact, and it's this kind of a many-body dynamics decides which atom is excited when and where, right? And that's what we kind of study. All right, no other questions? Is everything clear? Yeah.
What is the effective temperature of the system?
So it's a very good question. And this temperature can be defined in several ways, right? So first of all, we can talk about spin temperature. And so the spin temperature is determined by basically, you know, by basically like how well you prepare the initial state. So the absolute kind of gap, the energy gap between the separation between the two states which are involved in this process is actually huge. So it's a Rydberg state. So it's, I don't even know. It's like, I don't know. So it's involves two photons. One is blue and another one is infrared. So basically, the thermal occupation of this Rydberg state initially is, exponentially small, is extremely small. So basically what it means is that, and then we prepare specific states of atoms through the process which is known as optical pumping. And then in addition, we take these kind of images, so we kind of verify it. So basically our initial temperature is extremely close to absolute zero, spin temperature. And then what we do is we, of course, start, exciting our atoms. And then these spins, the spin degrees of freedom can heat up, in quotes, heat up due to multiple reasons. So one of them might be non-adiabatic excitation, right? So it's not a kind of a normal heating process. It's kind of many-body dynamics. So some of that I will talk about. So it's actually very hard to assign specific temperature to that. But then also our system is not completely isolated from environment. So during the excitation process, for example, some atoms can undergo spontaneous emission. And that doesn't necessarily create a thermal state, but it kind of is a kind of a heating process. So we try to keep this system kind of under control to the point that even in our largest arrays, we basically try to make sure that the probability to kind of for spontaneous emission of any one of these atoms, during this process is actually basically below 1. In the entire array. So the probability per atom is very small, but the entire array is small. But of course, there are all of these kind of decoherence effects which will come into play, which kind of do affect this evolution. So it's actually very hard to assign the temperature in this case. So, but it's extremely coherent. So it's from the point of view of external environment, is very close to being completely isolated. Then, of course, there is a kind of still there are motional degrees of freedom of the atoms. They are to the leading order decoupled from the spin degrees of freedom, but they're not completely decoupled. And so our atoms actually are not cooled. Their motion is not cooled to absolute zero. So that gives rise to, for example, like Doppler shifts. So I mean, these are the kinds of things which we are trying to control, right? But these things to a large extent are under control, but not perfectly. And we can maybe see a little bit of the effects of these open systems as we go on. All right, so there are 5 minutes left, but maybe I can already start. So basically, now I would like to kind of talk about 2 examples involving non-equilibrium dynamics experiments with these systems, and actually. One of them will involve kind of this near-adiabatic evolution across phase transitions, so in which case we will be talking and probing this so-called Kibble-Zurich mechanism. And the second example will involve kind of the opposite case where we just whack the system. We'll whack it very far away from equilibrium and try to see how it thermalizes, and there are basically some interesting things there to say also. But what I'd like to do is I'd like to maybe start with this first part. So talking about this near-adiabatic evolution, it's a new work which we are just finalizing, so it's not yet published, but it will be on archive maybe in 2 weeks or so. And this is actually a collaboration with theoretical groups of Peter Zoller and also with Subir, and actually Masei, Hannes, and Son Won, who many of you guys probably know anyways. They actually played an important role in both of these projects on the theory side. Okay, so let me kind of, I have this 5 minutes left, so maybe I will just try to introduce the subject and then we'll continue in the afternoon. So basically, what is Kibble-Zurich mechanism? So if you have a generic second-order phase transition, then we know that these phase transitions are basically characterized by some kind of diverging correlation length. So specifically, if you approach the phase transition, then the correlation length, for example, in terms of domain size in our case, should actually diverge, and it should diverge as a power law with some characteristic exponent. It's called mu. At the same time, of course, at the phase transition, the energy gap should also close. And the way how the energy gap closes is described by another critical exponent. That's the so-called dynamical critical exponent, Z. And actually, so if you, for example, the energy gap, here at the critical point will actually scale as a momentum to the power of Z. But actually, what you can do is, you can say, okay, so characteristic momentum here will be always on the order of this inverse psi. So you can just, plug this here, and what you will see is that in this case, as a function of, for example, some parameter, control parameter, which you change in the case of quantum phase transition, this gap should close as basically deviation from this critical point, where the point where a transition occurs, to the power z nu. And what is kind of important is that this nu and z are these critical exponents, which are sometimes called universal properties of the space transition. So basically, the phase transitions can be divided in different universality classes, and these universality classes are characterized by these two numbers, nu and z. All right, so what is Kibble-Zurek mechanism? So basically, Kibble-Zurek mechanism predicts non-equilibrium effects, for example, scaling of defects. If you go across a phase transition with finite speed, it predicts it in terms of these equilibrium critical exponents. So specifically, let's consider the situation where you kind of go across a phase transition and you ask a question, whether system will respond adiabatically or non-adiabatically. So clearly, if you are far away from phase transition where you have large energy gap, even if you go kind of with reasonably slow speed, nothing will happen. So the system will just, change adiabatically. But, clearly, at the same time, if you come close to this point of the phase transition, the so-called critical point, what will happen is that, since the energy gap here closes, you will start creating excitations. So what you could do, you can basically associate this kind of inverse energy gap with this so-called freeze-out time. So it's basically a time up to which like you can consider the system as kind of adiabatic, or not, right? And so clearly, since the gap closes at a critical point, this time will diverge here. And what this means is that if you now start, take your system and, for example, try to change some parameter of your system and try to go across this phase transition, then, eventually you will, if you go with the finite speed, eventually you will approach this point, this kind of, freeze-out point, where the system will stop being adiabatic. Now let's kind of, think a little bit, and so like when systems start being adiabatic, you start creating excitations and so on. So let's now think about in terms of like ordering. So let's say in terms of this correlation length, what is going to happen. So for example, initially our system is in disordered state, and initially when you start kind of approaching phase transitions, correlations will start growing. And if you approach your closer, the correlation length increases, and it increases even further. But then eventually, the system stops being adiabatic, right? And at this point, basically, the correlations cannot grow anymore as usual. And what this Kibble and Zurek kind of, postulate is the idea is that, like this, that whatever happened up to this freeze-out point will actually be the final result. So basically this, these domains grow, right, and they stop growing, and then basically even if, whatever happens with the rest, doesn't really matter, so basically the correlation length in the ordered phase stays the same as a kind of, as a freeze-out point. So this Kibble-Zurich idea has been an relatively old idea, and has been applied to all sorts of things, from cosmological phenomena to condensed matter systems. But actually, a decade or so ago, people realized that this idea might be actually applicable also to isolated systems, to quantum phase transitions. And kind of specifically, if you look, for example, at the Ising type phase transition, and you start, for example, playing with the speed with which you go across this phase transition. So that basically is, kind of this combination of these effects which I described. So basically, the correlation length will, be kind of maximized at this freeze-out point. You can express this kind of freeze-out point in terms of the speed with which you grow. So then, what will happen is that basically the final result is that this correlation length should grow as a function of this, time or inverse speed to some power which involves combination in mu and z. Yeah. And basically, what this means that, for example, for quantum Ising transition, there is a very well known prediction that this Kibble-Zurich exponent should be just 1/2. And that's actually very different, for example, from the kind of classical prediction. So if you try to write down some kind of mean field theory, which actually describes, something like Ising transition, then the Kibble-Zurich exponent will be 1/3, right? But in one dimension, for isolated system, you just cannot do this. So, but at the same time, actually, it turns out, even though this quantum Kibble-Zurich mechanism has been discussed and it's actually central to many kind of quantum protocols, to things like, for example, adiabatic quantum computation, it's actually very hard to measure this, and it's kind of several attempts have been made actually in cold atom systems, but it's actually, I would say, there has been no conclusive evidence so far that, you can really, measure exponents which are non-Mild field exponents. And so I will tell you, so I mean, maybe this is kind of a good point to stop here. So I will tell you in my next lecture how we measure these exponents and for Ising system, and how we also extend it to other more exotic systems. But maybe if there is a quick question or two about the Kibble-Zurich mechanism, maybe still there is some time to ask it. Or, yeah.
Once you freeze out, you get an excited state, but that's not going to be thermal, so there should be some decay time.
Well, yeah, that's actually a very excellent question, very good question. And the answer to this question, I can maybe give more complete answer, in an hour. But Kibble-Zurich is a kind of coarse-grained mechanism. It really does not tell you, what's going to happen there. I mean, it sort of assumes that the state will be thermal, and that's why it's a hypothesis, right? But we will be able to test it and see if it's true or not. Because actually, it turns out for our system is not completely true.
That temperature has to be higher than the thermal transition temperature.
So it's no. So this specific case which I'm discussing here involves isolated systems, where you can technically not even describe the temperature. The states we will create and not thermal. So I think maybe the original Kibble-Zurich mechanism was a little bit of this variety. Had used this kind of argument, but whether it's applicable to this case, I mean, it's not clear, right? But what we will see, I will sort of reveal the secret is that, sneak preview is that it turns out that in terms of coarse-grained kind of sense, this Kibble-Zurich scaling appears to be valid. However, the states which we create are clearly non-thermal, and there are some very interesting correlation effects which we can discuss. Yes. Yeah.
Like, why not just use like adiabatic perturbation theory or something? Shouldn't it give the same result as like the Kibble-Zurich theory?
So I mean, okay. So basically, I mean, these are generic kind of strongly correlated systems, right? Where you cannot use things like Bogolubov. I mean, they're non-mean field systems. So actually, it turns out that for this Ising case, there are versions of the Ising models which are integrable, right? There are versions which you can directly solve in terms of this kind of, you can convert them to fermions through Jordan Wigner and solve them. And people have studied this, and that's where most of these papers, initial papers, have kind of gained the intuition. So for this integrable case, indeed, you find that the scaling is similar to what is predicted by Kibble-Zurich. But also these kind of initial studies, which do it very carefully, they reveal some kind of non-trivial aspects, where they reveal this that you don't create actually thermal states. You have some kind of correlation between defects, which are kind of very non-trivial. And so in our case, the transition, the point where we cross the phase transition is an Ising class, but it's not along this exactly integrable point. And we will see if these predictions for integrable models will hold. Okay.